Test, test, test. Hi everyone, this is the lecture for Physics 102, March 30th. It's just going to be a relaxed lecture, live streamed to prepare for the test this Friday. And so let me just start off by showing you. I wrote up a little bit of a summary of the kinds of things you should be studying for the test, and it's on our Moodle site. So let's go there and log into our Moodle site. I'll show you where that is. Oh. And if you go to Physics 102, scroll all the way to the bottom there, you could see that along with our online notes, I've got summary for Physics 102. And what I did was there's really two major topics that we're studying. One of them is waves, and I guess you could say a subtopic of waves is sound, and the other one is thermodynamics. So all of that will be on the test. And I further broke it down into 10 discrete kinds of topics. So what I'm going to do is every once in a while I'll look over the chat to see if there's any question. Otherwise, I'll just give you some sort of sample questions that you might see on the test and go from there. Okay, so I'm just going to look at the chat, see if there's anyone. All right, looks like there's 3 people. All right, so whoops, I lost the. It's okay. Let me switch over to my whiteboard here. And the first topic we're going to look at is basically wave equations, and then just going to cut and paste the summary. There's the summary from from online. And what you should know about the wave equation is that it's a differential equation. It's a lot like the differential equation, second order differential equation for the simple harmonic motion. And you can see it written there up at the top, right there. Okay, and what it basically says is that you have this y, which is a measure of the displacement of, say, a string from its equilibrium position. And if you take and it's a function of both x and y, and if you take its second derivative with respect to x, and you take its second derivative with respect to y, they're equal to one another, but then there's also this factor in there, 1 over v squared, where v will turn out to be the velocity, okay? And the solution to the wave equation, it looks like this. It's the cosine, and basically there's both an x and a t component to it, and the coefficient in front of x is k, the wave number, 2 pi over lambda, and the coefficient in front of t is omega, and that's 2 pi over t, the period. And I'm going to show you in a second that if you actually plug that into there, you're going to get that k is equal to omega divided by v, and then if you plug in k is equal to 2 pi over lambda and omega is equal to 2 pi over t, or probably better, I should also add here, since t is f, that's going to be 2 pi times the frequency, and I'll show you that, whoops, that gives you the frequency. Okay, and so let's do that. So one of the questions I could ask here is I could say, all right, what's this equal to right here? What's that piece equal to right there? All right, so what's that equal to? And well, we know that y is equal to this. Let me just write that down like that. Y is equal to that. If I differentiate it once with respect to x, So we'll say dy by dx like that. You differentiate it once. What's the derivative of the cosine? Well, the derivative of the cosine is negative the sine, but then there's also this k in front here. So you're using the chain rule, you differentiate the cosine, then you differentiate with respect to x, and you will get that this is equal to minus k times a sine of kx. Okay, so there's the first derivative. If I differentiate it again, okay, so now I'm going to get d2y by dx squared. If I differentiate it again, what do you get? Well, the derivative of the of sine is the cosine, but then you also have to differentiate x with respect to x, so there's a k in front, so you'll actually get minus k squared times a cosine that. And if you look at this carefully, that is exactly the same as that. It's y. So really this is going to equal minus k squared times y. Okay, so let me just see if there's any questions about that. All right, there is a bit of a lag, so if you chat, there'll be a second before I actually see what your question is. But there's the second derivative of the solution, and that basically gives you the right-hand side. If you do the same thing with the left-hand side, what you're going to get is, well, now you're not differentiating with respect to x, but t. And here, you won't get the x there. You're going to get the omega in front. And so in here, instead of the k, you get omega, like that. All right. And if you differentiate it again, which is basically this, okay, but not with respect to x, but with respect to t, what do you get? Well, you get this whole thing again, but now every place you see a k, it's going to be replaced by an omega, like there and there. And so basically you'll get, you'll get minus omega squared a cosine omega t, which is going to equal minus omega squared times y. Okay. Now, why did we do that? Well, take a look. We now have this piece, and we have that piece. And so if we bring this down here, okay, the the left-hand side, I can replace it with this. The right-hand side, well, it's equal to that. But this piece here, I can replace that with this. And what you'll discover is, take a look at this carefully, the negative signs will go away. That negative sign there will go away, and that negative sign there will go away. All right. There's a y on this side, and there's a y on that side. They'll both, you can divide both of those out like that. And so basically you get this, which I can rearrange and make it look a little bit nicer by writing it as that. Okay. And you can take the square root of everything here because everything is positive. So you take the square root of that, you take the square root of that, and you take the square root of that. And what we've discovered is one of the first points about the wave equation. Basically, the wave equation with this solution gives you a relationship between k, omega, and v. And basically, it's that k is equal to omega times v. Okay? Now, I didn't draw the wave equation. It's hard to draw it in this whiteboard here. But if you now replace k with its definition in terms of lambda, like that. So here, this is, let me just take away some of those spaces there. Basically, k is equal to 2 pi over lambda. And you take out the omega, which is just basically equal to 2 pi f. And you divide that by v. You go, oh, that looks interesting. And now what can you do with that? Well, the 2 pi's will go away. Okay. You can multiply both sides by v. And you can multiply both sides by lambda as well. And basically you get this. Okay. So what does this say? This says that basically if you take the frequency, the wave equation predicts that if you take the frequency of a wave and you multiply it by lambda of the wave, you get the velocity of the wave. And since the velocity is a constant in this equation here, the velocity is a constant there. So changing F does not change V. Changing F will change lambda and vice versa. All right. So this is basically the conclusion from the wave equation. Now, what can you expect on the test? Well, on the test, you can expect me to ask you, what is this equal to? Okay, you can expect me to ask, what's that equal to? You could expect me to ask you, if you substitute into this, that you'll eventually get that. And you can expect me to ask you about this relationship here. Let me get rid of some of those spaces there, make it look a little bit easier to read there. That, and also this relationship here, okay? And then, of course, if you plug that relationship into this, that relationship there is basically just that relationship there, okay? So let me take a look in the chat here. Does anyone have any questions with that? Because otherwise I'll move on to the next problem. Okay, so make sure that you know how to differentiate the solution to the wave equation, and then differentiating it with respect to x to basically get minus k squared y, and differentiating it with respect to t to get basically minus omega squared y. And then if you substitute in for the second derivative there, substitute in for the second derivative there, what you're going to get is basically, and then take the square root, you're basically going to get that k is equal to omega divided by v. But k is equal to omega divided by v, that's the same as v is equal to lambda f. And we've done problems with v is equal to lambda f. In fact, I'm going to do one right now. Okay? So I don't see any questions in the chat. Let me go on. If you have a question, just put it in there, and if I have to go back, I'll go back. So let's just do a very simple example with v is equal to lambda f. The speed of light, that's 3.0 times 10 to the 8 meters per second. Okay, that's how fast light travels. Okay, and the wavelength of something like a microwave oven. Let's do a microwave oven. There's a lot of different, whoops, what did I do there? Okay, a lot of different things that we could choose, but I don't know. I'm just doing this off the top of my head. Say a microwave oven. Microwave oven has wavelengths which are about 5 centimeters in size. That's 0.05 meters, like that. And I want to know what's the frequency of a microwave oven. Well, this is really quite trivial, because all you do is just substitute into this equation here. So I'll do that very quickly. If I rearrange this equation here, basically what I'm going to get is that F is going to equal lambda divided by, V divided by lambda, like that. Okay, so basically take this equation, divide both sides by lambda to isolate F, because that's what we want to find. And what's V? It's 3 times 10 to the 8, like this. And what is your lambda? It's that. All right. And let me quickly bring up my calculator here. And that's going to be 3 times 10 to the exponent 8 divided by 0.05. It's equal to a really big number. I'll just put in all the digits there. Okay, there it is. And the units are going to be hertz, or per second. And now let's count how many zeros there are. There's 1, there's 3, there's 6, and there's 9. So it's actually equal to 6 terahertz. Okay? So that's a pretty big number, and we really haven't worked a lot with electromagnetic radiation, but there it is. Okay, so microwave ovens basically work in the 6 terahertz range. Or if you probably look at the back of the microwave oven, it'll probably have it in gigahertz, in which case you would see 6,000 gigahertz. Okay, it's probably a rating at the back there. Okay, so any questions with that? Let me see here. No questions in the chat. All right. I'm going to move on, okay? If you still want me to go back to this, I can certainly go back to it. But let's go on to point number 2 in the summary. So point number 2 in the summary was this here, standing waves, okay? So the theory behind standing waves is if you take a wave and you force it to be 0 at the end points, for whatever reason, and it could be any wave. In fact, microwaves in the microwave oven actually form standing waves. Okay, but the example that I gave in class is basically a string. So you take like a guitar string and you tie it down at both ends. This was the subject of the last lab. You don't get any old lambdas. You only get discrete lambdas. Okay, and as a result, this equation is still true. Okay, that equation is still totally valid. But if your lambdas are discrete, then your frequencies must be discrete. Okay, and discrete means you only get certain ones. You don't get a continuum. You don't get every value, say, between 1 meter and 2 meters or something like that. You only get like 1 meter or maybe 2 meters and so on. Okay. So let's do an example with this. So I'll just make something up here. Let's say that we have a string and we apply a tension to the string, and let's say the tension is, I don't know, 100 newtons. That's not too much. Okay, you could easily do that in a lab. And we're going to tie down, that's the capital L there in this equation here, is the how much of the string you're going to tie down. Let's say we tie down 30 centimeters, like that. That's going to be 0.3 meters. Okay, like that. That's how much is tied down. And I got to tell you how much the string weighs in order to get the linear mass density. Suppose that we have I don't know, we cut off 10 meters of this string. Okay, so we only tied down 30 centimeters of it, but I don't know, we went to the store and we bought like 10 meters of it. Okay, so that's quite a long string, and that 10 meters weighs, I don't know, 300 grams. Okay, so what does that mean? What does this tell you here? So if you know that 10 meters of the string weighs 300 grams, then the question is, how much does it weigh per meter? That's what this linear mass density mu is. Okay, so if you do, okay, it's 300 grams is 0.3 kilograms. Okay, and so that's your M right here. All right, and you want to know, okay, I've got 10 meters of this stuff, so what's that going to be? That's going to give me a mass density of 0.03 kilograms per meter. Okay, so it's a linear mass density because we're not dividing by the volume. The usual density, given the symbol rho, like when we worked with fluids, was mass divided by volume. But here we're doing mass divided by the length of the string. Okay, and so with the tension and with the linear mass density, you can now calculate the speed of the string. Now I know that standing waves, by the very name, standing, don't move, but there is in a sense of velocity to the waves in that string. And so even though you don't see the waves moving back and forth, they're kind of like bouncing off of the ends and interfering with themselves, forming this kind of a standing pattern. But there really is still meaning to the velocity. The velocity is given by the square root of t over mu. So we now have t, we now have mu, and so this is going to be the square root of 100 divided by 0.03. Okay, everything is in MKS units there. And let me do that on my calculator. I get the square root of 100 divided by 0.03. And that turns out to be 57.7. And everything's in MKS, so that'll come out in meters per second. Okay, so far, what have we got? Well, we've got the velocity, and that's this part here. Okay, I didn't mention this, but F1 is your fundamental frequency. This is the lowest frequency at which at which the string will vibrate. And so now we can calculate F1. That's going to equal the 57.7 divided by 2 times. And what's the length of the string that's tied down? So don't confuse this capital L, which is the length of the string tied down, with little l, which is just how much string we have. Okay, so like you could have 10 meters of it, but and we have 10 meters of it, but we only allow 30 centimeters of it to vibrate. Okay, so that L is the 30 centimeters, and 30 centimeters is 0.3, like that. And so what does that work out to be? And it's just a coincidence that this was 0.3 and that was 0.3. Okay, and so what does that work out to be? That's 57.7 divided by 0.6, and turns out to be 172.2. And what are the units for frequency? Per second or hertz? Okay. Now that could be one question. I could ask, what's the lowest frequency at which the string vibrates? But then all the other frequencies at which it vibrates are just integer multiples of that. And so you could say, okay, what's the next frequency at which the string vibrates? F2. That's going to be 2 times this frequency here. Okay. And what's that equal to? Multiply that by 2. Whoops. Looks like 344.5. Okay, there's a little bit of a round off error like that. And I'm not going to do any more. For F3, it would be 3 times that and so on. Okay, so let me look in the chat here if there's any questions. Okay, 5 people watching, and doesn't seem to be any questions in the chat. Okay, so there is a 30-second delay. And if there are no questions with this, I'll just move on to the next topic. And if you do have a question on this and I see it later, I'll just come back to it. Okay. So there's a typical example of a question for standing waves. So I didn't write it down, but basically, let me just repeat it again. I give you a string with tension 100 newtons. We tie down 30 centimeters of that string. It turns out that 10 meters of the string weighs 300 grams, and I want you to find F1 and then all the next higher frequencies, okay? And so the first thing to do is for F1, you need that velocity, which is the square root of T over mu. Mu is the mass divided by the length. So I gave you the length and the mass there, and it's going to be 300 grams is 0.3 kilograms divided by 10 meters, or 0.03 kilograms per meter. Plug that into the square root, and it turns out that the velocity is 57.7 meters per second in the string. So F1 is going to be the 57.7 divided by 2 divided by capital L, which is how much the string is tied down, 30 centimeters. That gives you the lowest frequency. The next one is twice that. The next one is 3 times that, and so on. Okay? So there we go. That is standing waves. Another thing that we looked at was beating. Okay, now it turns out that both standing waves and beatings, how are they related to this wave equation? It seems like the wave equation just came out of nowhere. I tried to give you a little bit of a derivation of how it came about. I didn't give you like every detail, but you know, the one of the properties of this wave equation is that you get superposition. That means if you have one wave which is a solution, you have another wave which is a solution, then the sum of the two is a solution. Okay, with standing waves you can't really see the two solutions, but it's as if the two waves were kind of like bouncing off of the walls and then superimposing with one another. With beating, it's kind of the same thing too. It's a superposition, but now it's a superposition of two different frequencies, F1 and F2, and this is done in guitar, like with guitars, like to tune strings in a guitar or violin, or not so much a piano where you tend to use a tuning fork. But in the guitar, you know, when like you put your finger on fret 5, when two notes are the same, you won't hear the beating. But if they're slightly off, then you'll hear the beating. And basically what beating is that you have these two frequencies, and they're very close to one another but not equal. When you play them together, the frequency of the note that you hear is actually the average of the two. Okay? But they don't just sit there at that frequency. They actually go loud, soft, loud, soft, loud, soft. The frequency at which you get the loud, soft, that's the beating frequency. It's basically just the difference between the two. The reason I have this in absolute values is because it doesn't matter which one's bigger and which one's smaller. Okay, so here's a really simple example. Okay, let's do, oh, I don't know. Um, I don't even know what notes are, but I think there's I think high A, like one A above middle A, one octave above middle A. I think the frequency is 220 hertz. Okay, so I think that's a note. That's like a high A. And then suppose we have another string, and it's just slightly out of tune, and it's playing 222 hertz. And I can ask the question, what's the frequency of the note you hear? And it isn't this note. You don't hear one note, you don't hear the other one, and you don't hear them distinctly. They somehow mush together, and what you hear is the average of the two. Basically, you hear this, and that's pretty easy because that's just 220 plus 222. divided by 2. In other words, you hear 221 hertz. Okay, so that's the note that you hear, but it's not a steady note. It goes loud, soft, loud, soft, loud, soft. And so I can say, what's the beat frequency? And that's this. Okay, that's the beat frequency. And basically, it's just the difference between the two. And if you take 220 minus 222, that's pretty obvious. It's 2 hertz. Okay, so basically, if you play a 220 hertz note and you play a 222 hertz note, you will hear a 221 hertz note, which goes loud and soft 2 times a second. Okay, so it beats pretty fast, actually. All right, so let me take a look in the chat. Any questions? Steph. So, back to that one. So L is the length of the string tied down, and lowercase l is the length of the string totally correctly. Yes, Steph, that's exactly right. Yeah, Steph, I know you said wait there, but that's the way it goes. So I'm going to just bounce back for a second. So let me put beating aside for a second. Let me go back to Steph's question. So here at the standing waves, we've got two L's. We've got that L, capital L, and we've got lowercase l. Lowercase l is like is the length of the entire string. Okay, so like you go to the store and you buy 10 meters of the string and it weighs 300 grams. That's right. So that's capital L. It's like the total length of the string. But just because you got a string which is 10 meters long doesn't mean you tie it down 10 meters away from one and like one end and 10 meters away from the other end. We're only going to tie down 30 centimeters of it. Okay, and so capital L is just how much that actually vibrates. Okay, so I think that answers your question, Stephanie. If not, just ask again, and I'm going to go on. Okay, so and I apologize for this 30-second delay, but at least with the live stream, this will be up later. You'll actually see even your own questions in the chat, and everything will be recorded, and so on. So it was a little bit better than a Google Hangout. All right, so that was number 3, beating with 2 notes. Okay, so let me just look here. Any more questions? And all right, let me go on to number 3. So number 3 was basically yet some other phenomena. Like again, everything hinges off of this wave equation, all right? And without proving everything, standing waves comes out of it, beating comes out of it, and so do these guys here too. But these ones are even harder to show because these guys are basically some kind of like they really require 2 dimensions and more, and that's beyond the scope of this course. But basically, waves will reflect when they hit a barrier. So what happens? Waves reflect when they hit a barrier. How do they reflect? Well, if you form this ray, which is basically the direction in which the wave fronts move. Maybe I can try to draw it here. I don't know how well this will work out, but like if these are like what you're looking at there, those vertical lines, they're crests, okay? And the ray is basically the arrow that points like this, okay? It says, oh, those crests are moving in this direction there. So if you follow that ray as the crests hit a barrier, the angle of the incident angle is equal to the reflected angle, okay? That's about all you can say with reflection, and it's not very deep. Okay, so with particles, you actually get the exact same phenomenon. Okay, so reflection, whether it's with waves talking about the ray, which is this piece right there that I've got highlighted, or it's particles, which is basically their trajectory, the incident angle is equal to the reflected angle, period. Okay. The other one is, actually, let's do diffraction next because there's no formula for diffraction. Well, no formula that I gave you for diffraction. It's a fairly complicated formula. But diffraction is basically this phenomenon that when waves encounter a barrier, or something like a sharp edge, they'll bend around it. Okay, so basically waves will bend around corners. And in the lab that we skipped, at least in my section we skipped, you would send these water waves towards a barrier, and then you could definitely see that as they go around the barrier, they tend to curl, okay, and then eventually they heal up, okay, and so that's reflection and diffraction. Basically, with those two, all I can do is ask some qualitative question. One other thing about diffraction, qualitative question, is that diffraction happens if waves go through a hole. Okay, but if the hole is much smaller than the wavelength, well then none of the wave gets through. Okay, so you got a hole and it's got a size, the size of the hole is much smaller than the wavelength, waves will not get through. If the hole is much bigger than the wavelength. Then you get not a perfectly sharp shadow, but you get a sharp shadow. It's when the hole is about the size of the wavelength that you get a kind of this circular pattern that emerges on the other side. Okay, uh, in diffraction, that's how microwaves are kept inside of a microwave oven. You know, if you look at you can see inside the microwave oven through the front door, and if you look, there's a screen, and it's got these little holes, and these little holes are about, no, maybe a couple of millimeters in size, but the wavelength of the microwaves is about 5 centimeters in size, and so there's no way those 5 centimeter wavelengths will diffract through a 1 millimeter hole. Okay. And so basically the microwaves won't get through, but visible light, which is also a wave, it gets through no problem. Okay, and the shadows are even fairly sharp because the hole is much, much bigger than the wavelength of the visible light. Okay, let's look at refraction. So refraction occurs when a wave travels from one medium into another medium. Okay, and the speed of the waves changes from one medium to another. So back to the wave equation here, v is a constant. Okay, it is a constant, or better yet here, it is a constant, but within one medium. Okay, so if you switch from one medium to another medium, the speed of the waves changes, and when the speed of the wave changes, it causes the wave to refract, and basically there's a bending of the rays. Okay, and the rule is that the ray bends towards the normal in the medium where with the bigger n. Okay, so let's take a look here in the chat if there's any questions. All right, I don't see any questions. Let's do a problem with refraction. All right, and so a little hard for me to draw, but let me just try to describe this. Let's say we have, what did we do in class? We did air and water. Let's do air with an index of refraction, let's call that N1, which is 1, okay? And glass has an index of refraction of 1.5 approximately, depending on the type of glass, okay? And let's say that you have one angle. The angle in air is going to be, I don't know, let's make it 30 degrees, like this. All right, so there you go. And I want to know, what angle does this make in the glass? All right. What angle do you get in the glass there, like that? All right. So I can't draw this, but what you would see is, you know, this ray, and it comes up to the interface between the air and the glass, and the ray is going to bend, and it actually bends towards the normal in the glass. So you expect, because n is bigger in the glass, you expect theta 2 to be smaller than theta 1. So this angle had better be less than 30 degrees. Okay, so let's do that. Here's our equation. All right, let's see. Okay, there's our equation. For N1 there, we're just going to substitute 1. This is the index of refraction of air. For theta 1, we're going to substitute 30 degrees, like that. Okay, for N2, we're going to substitute 1.5, like that. And for theta 2, well, we don't know it. That's what we're solving for. Okay, so now if you do the sine of 30 degrees, that turns out to be 0.5. So you get 0.5 is equal to this. Okay, divide both sides, okay, by 1.5. So you get 0.5 divided by 1.5 is equal to the sine of theta 2, like that. And what does this equal? Well, let me just do it on the calculator. 0.5 divided by 1.5, that's like a third. All right, whoops, something's going back here. And then what you want to do is you want to take the inverse sine of that, and you get 19.5 degrees. Basically, theta 2 is 19.5 degrees. All right, let me see if there's any questions in the chat. Nope. All right, so there's an example of making use of Snell's law. All right. Now there is another phenomenon with Snell's law that we should discuss, and that is total internal reflection. See that you know, now we can go here, and we know that that question mark is 19.5 degrees. Okay. Now here's the thing: the angle in the glass is always smaller than the angle in the air. So what if we shine the light from the glass into the air? Well, then you can get into this very strange situation where in the air you actually hit 90 degrees. And you wonder, at what angle will I hit 90 degrees in the air? And that 90 degrees is important because that's where total internal reflection begins. And what total internal reflection means is that the light no longer connects at the glass. Okay, so now we're shining the light from the glass into the air. Over here in the first problem, we were shining the light from the air into the glass. Okay, but now we're shining it from the glass into the air. At a certain angle, which is less than 90 degrees, the angle in the air becomes 90 degrees. Okay, and then beyond that angle, there's the light just cannot leave the glass. It basically reflects internally completely. Well, that's an easy one to do. You just put in 90 degrees for the angle in the air. So you start off with Snell's law here like that. And the index of refraction for the air, that's 1. What about the angle in the air? We're at that critical angle, so this turns out to be 90 degrees. Okay, and N2 is 1.5. Okay, and we want to solve for theta 2. Theta 2 now is a special angle. It's actually the critical angle, like that. And sine of 90 degrees is 1. Okay, so you get 1 is equal to 1.5 times that critical angle. Okay, divide both sides by 1.5, take the inverse sine. All right, and so I'm going to skip those details, but I think you know how to do that. That's not too hard. And so you get degrees like that. So at this critical angle, total internal reflection occurs. Okay, when the angle in the glass, so this is theta in the glass, this is like theta 2. At angles where theta 2 is less than the critical angle, you get refraction. Okay, but at angles which are bigger than the critical angle, the refraction turns into reflection. Okay, and so there's this transitional this transition that occurs. This can only occur when you're going from big N to small n. It never occurs the other way around. Okay, so let me look in the chat because I'm done with refraction. Any questions? Doesn't seem like there are any questions. Okay, so that was one of the things. So now we looked at reflection, we've looked at diffraction, we looked at refraction. Let's look at interference. Interference is a little bit more complicated, and that actually involves these two equations. Let me actually cut them out of there. And let me paste it down here like this. Okay, and there's two types. There's single slit, okay, and there's double slit. All right, so basically when you send light through, I'm thinking of light because that's the easiest experiment to do in the lab. You just basically use a laser, but you could do this with water waves or whatever. But you know, if you take waves and you pass them through a single hole, all right, so that's what we mean by a single slit, and the size of the slit, which is A, is approximately the size of lambda. So these two, they don't have to be equal, but they have to be roughly the same size. Like if this is a meter and this is a nanometer, well then there's going to be no phenomenon here at all. Okay, you're not going to get any kind of diffraction or interference. But if this is like in nanometers and that's in nanometers, well then you're going to get some kind of an effect. Okay, but if you have a single slit, this equation here will give you where the angle at which the dark bands occur. Okay, so that equation will give you the angle at which dark bands occur, and this n, this is basically an integer value. Okay, so it tells you whether you're talking about the first band, the second band, and third band, or so on. Okay, so once again, A, that's the size of the hole. Theta, that's the angle at which one of the dark bands occurs. N, that's an integer. 1, 2, 3, and so on. And lambda is the wavelength of the light. Okay. Now you can repeat this experiment and you can do it with a double slit. All right. So with double slits, these are two slits. The size of the hole doesn't matter as much. Again, the hole has to be roughly the size of the wavelength. But what really matters is the distance between the holes. So here I called it in this equation D. The two equations look a lot alike, so they're often confused. But here, D, that is the distance between the two holes. Okay, theta is going to be the angle at which either light or dark bands occur. Okay, but it depends on what m is. Okay, so m, if you put m in this equation here, if you put m is equal to an integer, you get the bright bands. If you put m is equal to a half integer, you get the dark bands. Okay, so you can see how this could be confusing, because here integers correspond to dark bands, but here integers correspond to bright bands, and it's the half integers that correspond to dark bands. And if you wonder what do I mean by a half integer, that's like a half, 3 halves, 5 halves, okay, and so on. Anything which is like, you know, it's a half off from an integer value. Okay, they're called half integers. All right, so let's do a problem here. Let's use light again, and say light. Whoops. Light has a wavelength of about. Let's do, I don't know. I guess this is kind of greenish light. It's 500 nanometers. Okay. So we have light, which is 500 nanometers. And let's do the double slit experiment. They're both kind of similar, but the double slit experiment has more possibilities. So let's do the double slit experiment. I'll leave that one off for you to work on. And let's say the distance between the holes is going to be, let's make it 2 micrometers. Hold on here. I need a micro from somewhere. 2 micrometers. Okay, so these are typical sizes down at wavelength of light. And if you don't remember nano, nano is 10 to the minus 9. Okay, and micro is 10 to the minus 6. All right. So, you know, when you're working with something like light, you know, you're working at these sizes like that. All right. And here's my question. At what angles do the bright bands occur? And maybe I should just preface this. Maybe I should just preface this and say double slit. Right. So there's no confusion. I'm not talking about a single slit here. I'm definitely talking about double slit, and I want the angles for the bright bands. Okay, so it's this equation here. All right, it's that equation there. And these m's, you say, well, what m's are allowed? They're integers, right? For bright, you want integers. And you say, what integers? 0, 1, 2, 3, and so on. Okay, you can even do the negative ones, but the negative ones just give you the negative of the angles for the positive ones. So we'll just do the positive ones. Okay, and I wouldn't ask you for all of them. Maybe we'll just do a couple of them. Like maybe we'll just do these two. Okay, so now you say, well, what do we do here? Well, D is going to be 2 micrometers. Okay, now you know, we could convert them to meters, but just notice something here. A micrometer and a nanometer. There are 1,000 nanometers in a micrometer. Okay, I hope you see that. So, you know, if we were doing this, if you said, how big is 1 nanometer? Or sorry, 1 micrometer. A micrometer. The micro is bigger. Okay, nano is smaller. And how much is it smaller? The nanometer is a 1,000th the size of a micrometer. So 1 micrometer is 1,000 nanometers. Okay, now why did I do that? Well, because here D, I gave it to you in micrometers. I'm going to just write that as 2,000 nanometers. Okay, all right, and then I've got sine of theta there. All right, and after all, we're solving for theta because I'm asking you at what angles. So as soon as you hear at what angles, you're thinking theta, all right? And now m, you say, well, which one do I choose? Well, let's start from the middle and work out. How about we put 0 there? And then we have lambda, and lambda is 500 nanometers. Well, let me get rid of some of these spaces there. It looks ugly. Okay, well, look, if you got a 0 here, this is equal to 0. So all you get for the first one is sine of theta is equal to 0. And at what angle does 0 occur? Well, it's 0 degrees. Okay. So what does this tell you? Let me put it on the next slide. Okay. What does this tell you? There's always a bright band at 0 degrees. That's basically what this is. There is always a bright band at 0 degrees. All right. Well, that was kind of trivial. Let's do it again, but now we'll do it for the first bright band, which is on either side of the middle bright band. Okay. Remember, there's a bright band, then there's a dark, and then there's another bright. And the second bright there, that's the number 1. So it's basically this equation all over again. Okay. But now, instead of a 0 there, we have a 1. All right. And now we have 2000 times sine of theta is equal to 500. So that's going to give you 2000. Oh, I made a mistake. Hold on here. Oh, I'm sorry. No, I didn't. I apologize. I apologize. So we want to divide. I was about to divide the wrong way. Okay. So that's going to be 500 divided by 2000. And what's that equal to? That's like 5 divided by 20, which is 0.25. Okay. And so if you do the inverse sine of that, I get 14.5 degrees. Okay. And that's the uh, m equals 1 bright band. Okay. Now I'm not going to do m equals 2 because I think it's pretty obvious. You just put 2 in there and then 3 and so on. And you can get all the bands. All right. But what I do want to do is I want to ask another question. I did the bright ones. How about at what angles do the dark bands occur? All right. And it's still this equation here. All right, still that equation. But now what's m equal to? M is going to equal a half, 3 halves, 5 halves, and so on. Basically, just it's an integer and then lop on a 0.5. Just add a 0.5 on there, okay? And so let me just do the first dark band. It's this equation here. Well, yeah, this one here. That's right. Okay, and not 0.1 though, but 0.5. Okay, so why 0.5? Well, we're looking at the first dark band, and there it is. Okay, so 0.5. And so now this is going to be 2000 times sine of theta is going to equal 250, like that. And that gives us that theta is equal to, I'll do that for you very quickly on my calculator. Oh, what did I just do? So we get 250 divided by 2000. Then the inverse sine of that is 7.2 degrees. Okay. Let me look in the chat if there are any questions. And no new questions. All right. So let me just see how much time do I have. Actually, I'm out of time. This is the 15 minutes. So how far did we get? We got through up to 4. All right. So it does look like there's a lot of topics online, but actually we already got through points 1 through 4. There's 5. 5 is the inverse R squared law, 6 is the Doppler effect, and then thermometers, ideal gas, specific and latent heats, and then the second law of thermodynamics, okay? And those are all the topics that are on the test, all right? So I'll stop here for now. I will have our Google Hangouts tonight. If I get more than 10 people, then I might get in trouble. I might just ask people to switch over to a live stream. That shouldn't be too hard to do. You could actually do both at the same time. But we'll see how it goes. And then Wednesday, I will, finish off the review. Okay. And well, that's it, guys. I'll wait just a few more seconds, and to see if you guys chat anything in the text chat there. If there's any other questions, otherwise we'll just end the stream. Oh, and I'll put these review notes up. I'll just put summary. I'll put sample questions, review sample questions. I'll put that up on our Moodle site. In fact, I'll do it now while you guys decide whether or not you want to. have any more questions. Actually, I can't right now. I'll do it later. I'm sorry, guys. All right, you know what? It looks like there are no more questions and people are leaving the chat. So why don't we call it a class for today? And well, that's it. Thanks, guys. We'll see you on Wednesday.